Hello, welcome to the part 3 discussion of 8086 microprocessor. The first two parts were given with respect to the features and architecture details of 8086 microprocessor. Then the discussion was continued on register organization of 8086. In the architecture representation, if we look, we have just seen the lower section of this architecture with complete details represented with an overview of execution unit. One more peculiar block that makes a point of interest in the upper region is addresses are generated in the format like this. We have 16 data line capacity and 20-bit address line capacity here. What's the strategy of 8086 microprocessor is, though it generates a physical address of 20 bits, it will operate only with an address capacity of 16 bit. How is this 16-bit address capacity being operated? This is done newly with respect to 8086, which is for the first time in 8086 architecture. So if we can look over these known names, ES, CS, SS, and DS code segment address register, stack segment address register, extra segment address register, and data segment address register, how their arrangement is being given can be explained through a simple example. The representation is something like this. 8085 has 16-bit address lines through which it is going to address up to 2 power 16 locations shown as 64 kilobytes or 64 KB location. Each location will be having a capacity of 8 bits, and the address is represented with a format of 16-bit or 4 hexadecimal representation. Showing the range for 8-bit memory mapping is 000H to FFFH. According to 8086, if we copy the same discussion of 8085, 20-bit address lines in physical are available through which the memory mapping should be done from 2 power 20 lines going for a memory arrangement of 1 MB locations. How simple the representation will be. With respect to 8085, the data capacity is 8-bit. With respect to 8086, data capacity is 16-bit. So we can go like each location should hold a data of 16-bit. But this is not what actually is happening with 8086, both in data storage and address representation. If we see that each location is represented in address format using 20 binary bits or 5 hexadecimal numbers. The address range actually is 00000H to FFFFFH. If this is the strategy, what is the discussion or what is the problem here? No, 8086 has a different view. It says like using less number of address lines, using 16-bit address lines, it is going to map a memory of 1 MB. Whereas the rule that we have learned is using 16-bit address lines, we are mapping only up to 64 KB. But due to some presentation, that is due to some innovation in 8086, we can see like using 16-bit address lines itself, we can map up to 20-bit address lines, and by through which we can go up to 1 MB of memory. A simple example most probably represented in many textbooks is, let us take an area which is having some plenty of houses, and let us say we have to deliver some information or a post to one of the house in these 20 location examples. For example, we have to deliver a post to 16th address here. So how shall we start the counting again is from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Somewhere after counting 15 locations, we will reach definitely the 16th address. Success rate is 100%. Problem is, if we are having the post to be delivered for first address, how quickly it happens. If we are having a position of delivering the post to 19th house, how much time it is consuming. So how can a memory show differentiation in memory mapping arrangements? So for this purpose, a small strategy is applied in this example is, you let us arrange all the houses in a pattern so that it will save our time. How is this pattern shown? Like this. Something. Saying like don't arrange them all in a same order, make them in a division of 5 for each arrangement. Saying like 5 houses for one row. the condition is like this. Suppose I want to go for the 19th house, somewhere here will be the 19th house. So I need not check all these locations. I can skip first road, second road, third road. I can directly go to road number 4. I need to check only 3 houses. So I will save a time for around 15 locations. So this time saving capacity is called arrangements. The same strategy is applied with respect to the memory allocation or address allocations. You need not count for 20 addresses. Totally, actually, we have 5 plus 5 plus 5, we have 20 addresses, 20 houses. Same thing. But what is that we are doing is saving time in addressing each house here. The same concept is applied for memory also. The example is again explained in detail, saying like, if these are the locations, we have 4 locations for example, and each location is having a 2-bit capacity. The addresses that will be generated will be like this: 2 power n here is 2, 2 power 2, 4 values. So 2 bits are used for addresses. Why? Based on the number of locations. Now if we enhance like this, same 4 locations, 4-bit capacity. We need not increase our addressing capacity. Addressing is not matching with respect to the size here. Address is increased with respect to the number of locations. So if we increase the number of locations, what should we do is increase the address lines. How? It happens like this, as shown. So from 2 bits, we have increased the addresses to 3 bits. So still, if we enhance from 8 locations to 16 locations, every time the architecture should have to manipulate its physical address line capacity. So instead of going for this change, if we can provide a strategy like using only 2 address lines, I can map up to 8 locations. The example is provided like this. Divide your memory into some blocks. Logical blocks, not physical, logical blocks. Considering like how much capacity do we want? We want only 2 address lines to be utilized. So how much possible memory locations can we go up to 2 address lines is 4. So we will divide our memory in this example as 4 locations per block. So we divide it into blocks. So how many blocks we have framed in this example is 2 blocks. And what are the addresses we are generating? Only 2-bit. Minimum range is 00, maximum range is 11. So if I say I want an address call 10, we have 2 locations. Which 10 we want? We will say along with that 10, generate your road number, or saying like block number. Now together with a combination of this block number and this generated address, we call this address as program address, or we call it as logical address, or we call it as offset address. And these are called block addresses. The other good name, technical name for blocks is segments. So this concept is making our memory into segments, and moreover these are all logical segments. They are not physically been arranged. Based on the view we are seeing the locations. We don't see the complete memory as a 1 MB location. We will see it as parts of 1 MB. So based on this strategy, we will be having some representation, saying like if you want your address, for example, I want the 6th location here, saying like how to generate the 6th location. Generate the program address first, then identify in which block you want to go. So you need not search all these locations. So this much memory area is skipped for searching. If this concept is not there and only this concept is existing, so we need to search for 6 locations. Now we are saving the time. This concepts help in 2 ways. One is saving the time, another is generating only few addresses, still mapping to the higher memory locations. This concept is newly introduced from 8086 and it is still running in our days. This is why we are easily enhancing our hardware memories in the computers, saying like we can go for 1 TB hard disk to 2 TB hard disk easily. We can add pen drives to our computer. We can add any other external hard disk. Still the memory is working in the same capacity. How it is possible? It is not viewing it with a complete set of 1 TB or 2 TB. It will be seeing it in a parts. How? The actual address will be the actual address will be the combination of segment address and program address. So this is what we call as physical address, and these are called as segment addresses and offset addresses. So the relation is explained like this. Physical address is sum of segment address and offset address. And this is happening with a black color box we have seen in the architecture as memory segmentation blocks. The size of each segment in 8086 is 64 KB with respect to 16-bit offset address. The capacity what we said in 2-bit earlier is now 16-bit physically in 8086. And segment address and offset addresses are given like this. Sometimes the segments are isolated to each other. Sometimes we might have the segments overlapped to each other. So how actually the working of the physical conversion using logical addresses is done is something like this. Though it generates a 16-bit logical address, it can map for a 1 MB of physical address. So what is the relation explained here is the 20-bit physical address is generated by a combination of 16-bit segment address, which is multiplied with the 10H in the sense 16 locations, and offset address. This address mechanism will help in generating the 20-bit address. What is the range of 20-bit address? 00000H to FFFFH. Still, by using these two addresses, we can generate a physical address. And what is the range for them is only 16-bit. Still, you can see the range varies with respect to segment address here. So using this, if we perform a simple example, find out the actual address by generating the program address of this and by generating the segment address of this, and it happens something like this. PI is equal to SA into 10H plus OA, offset address. So the mechanism is given like this. The same mechanism, if it is detailed in binary format, the 1000 is written in this format. After multiplication with the 10H, we are giving a 16-bit displacement, or nothing but 16 position displacement, nothing but displaced by 4 bits, making it into a arrangement like this. Finally, we get our answer in this pattern. So if we have a simple practice on all these things, given addresses, finding out the physical address. First one is very easy. The final physical address will be 12345. Then it will be 12,235H, or we can speak the other one as 18555H. Looking into the last one, the segment address range is exceeded, so it is not suitable for finding the physical address. So these are some practice arrangements which will help us in understanding the memory segmentation concept. So if we have the final capacity saying like maximum segment address and maximum offset address, if we give, we are going to get the maximum physical address. So this is the way the mapping happens. And to support this mapping, all these segments will be classified into code segment, data segment based on the representation, stack segment and extra segment. These segments will help the user to store the required data in respective segment. To operate these respective segments, we are using their respective segment register. And these are combinations like code segment will take the inputs and data segments will take the output arrangements mostly. So this is the way how they are being shown as. So code segment or data segment, code segment and data segment takes the inputs. Extra segment is used for output storage, ES in combination with DI and DS in combination with SI. So these are the representations. So how internally things could help us. So segment address, starting address plus some displacement, 64 KB displacement. Data segment address, some starting address, segment address, then 64 KB displacement. So these are the outlooks we can show with memory segmentation, which is newly developed from 8086, and it is standard till now for any Intel product microprocessor that is being developed. With some more extra features, specialties of 8086, we shall meet in the coming discussion. Thank you for this.